At Cornell University, physics department, all graduate students have to take a lab course called 510 lab. And obviously, theory students are very unhappy with that requirement. And many theory students want to avoid that. And they were always told for a number of years that look at Professor Dyson, who was a graduate student at Cornell but never got a PhD. With the implication as theory students will read what it means. So finally, we decided to check it out with Professor Dyson in one of his visits to Cornell. Did he pass the course? And Professor Dyson told us that he took the 510 lab and he passed it. So that's not the reason that he didn't get his PhD at Cornell. So yes, other reasons. Okay, so today I'm going to talk about a topic which I've been working on the last couple years in Hong Kong. But before I start this, I would introduce the university to you. This is the campus where we got to see from the new building that we are at, the new IS building. So we just moved in this summer, but we still need to do some work inside before we can really start welcoming people. So the topic of my talk today is done with the work with our postdoc, Yosuke Sumitomo, and more recently with a graduate student. I don't have to go through the dark energy, dark matter issue because Professor Wang have gone over that. So our universe is mostly, in terms of energy content, is in the dark energy. And I'm not going to explain what dark energy, dark matter is, but essentially there's very strong evidence that we are living in a de Sitter-like vacuum with a positive cosmological constant, which is what we call the dark energy. So we call it Lambda. And Lambda contribute to about 70% of the energy content in the universe. And obviously, it's something that we have to worry about. In fact, that percentage will continue to grow as the universe gets older. In terms of the setting C equal light 1 and h bar equal to 1, we can express the Newton's constant in terms of Planck mass. That's the natural scale of gravity. And in terms of the natural scale, the cosmological constant is an extremely small number. Okay? And the question is why it is so very small. That's the puzzle we like to discuss today. Okay? There's many proposals in trying to change the accelerating universe discussed by Professor Wang that is not due to a cosmological constant. And I think those possibilities are very interesting to explore. Is there any other way that they can be explained, the data so far? Okay. Even though the data very strongly suggests that's the value. But in all those proposals, you may have heard of quintessence, chameleon, modified gravity. In all those proposals, they still have to ask the question, why lambda is so small? Because in their case, lambda is even smaller than this because the accelerating universe is due to some other mechanism. So this question is present in all these other possibilities as well. So in Einstein's theory of general relativity, we know that we can always add an arbitrary constant or the cosmological constant into Einstein's theory, as Einstein did it once himself. And we can always fine-tune that value to a very small value to fit our observation. That can always be done. But the question is, why so small? The other possibility is what some of the cosmologists nowadays will refer to the anthropic principle. I mean, a strong version. Not that so that to describe universe, but that the only way is that nature have to pick such a small value such that we can be around to observe it. Okay? And that's those are the two ways to justify why we have a very small cosmological constant within Einstein theory. However, we know in string theory, and I should say that even though you are not a string expert, that's still okay, because we all need is the very basic points of string theory today. And in string theory, lambda is a calculable number. You find any solution to string theory, you can, in principle, calculate it. And so string theory is the place to search for explanation that's beyond the anthropic principle. Okay? I would like to also point out that our universe probably have gone through some inflationary period where the effective vacuum energy is much, much bigger. So that means that we end up today a very small cosmological constant by evolving to it, and not because we have been sitting there from day one. Okay? So that means that it has to be dynamical in some way. Okay? And as we would like to point out that string theory has no free parameters. So in principle, everything is calculable in string theory, although there's many, many possible solutions. And question is why these solutions select the particular universe we have. And that's a question which beyond my talk today. Okay, so first I want to point out a very interesting and important property of string theory, and that's noticed by Busa-Paczynski, that all the fluxes, for example, electric fluxes, we know electromagnetic fluxes, but all fluxes in string theory are quantized. Okay? That means they take discrete values. So the particular example they give is that if cosmological constant is equal to some negative Bayer value, plus fluxes wrap around values with different integers. So n will be different integers, and q will be the effective charges. Okay? And you have enough number of terms with different qi, and n can run over, say, from minus 1,000 to 1,000, or minus some number to a plus number, depends on what you want to do, is that you will find that if you have enough number of terms, then the spacing between the different values cosmological constant would be very, very small. The spacing is small enough such that it can be take value of 10 to the minus 122, or even smaller. Okay? That way, they can accommodate a very small cosmological constant within this framework. Okay? So the quantization of the fluxes essentially means something like this. There's some potential in the flux units, some flux, and they have values, integer values only, and you can tunnel from one to the other one by some, say, charge annihilation, brane flux annihilation processes. So essentially some barrier. And so these are the quantized values in one particular flux. And in string theory, generically, we're going to have order of hundreds. So it's important to remember that we can have hundreds of fluxes in a particular solution. Okay? So there would be many, many possible solutions. And Busa-Paczynski told us that it's possible to have a very small value. But the question is why nature picks such a very small positive value. Okay? That's the question that we want to address. Why maybe cosmological constant is small in a natural way within some string theory framework. So we would like to argue that there's a statistical preference. Okay, not a particular solution, but we look at a large set, the statistical preference for very small, either positive or negative lambda. Okay? And we illustrate with some examples. Okay? So in general, consider a low energy effective potential coming from string theory, where the potential will have a lot of two-form fields, which we call B or C. Okay? We sometimes call Ramon, Neuer-Schwarz, and they will have three-form fluxes, essentially the curl of these fields, so which we call F3 and H3. And these will wrap cycles in some compactified manifold that generate our four-dimensional theory. And these fluxes are quantized So what we have is we have a potential of this form, B2, C2, and with a set of light scalar field Ui. Okay, these scalar fields are typical the ground state of the string tower scalar fields, like Higgs fields, but many of them. And so the potential can be written in this form. That means potential is function of the fluxes which are discrete. Okay? They're not integer because they're linear combination fluxes with different detail, but they are discrete fluxes which take a range of values. Okay? So this is generically the potential we will end up from string theory, particular compactification. So what we're going to do now is look for metastable solutions of this potential. And what we do is fix a particular set of nj. Okay, they're fluxes. We fix them, okay, because they are sitting in a local minima in those flux directions. And then we'll solve for the ui. That's essentially the same as the, you have a potential, and you solve for them. And then the ui will be functions of the nj, given by this. And we get the minimum of the potential, which is the vacuum energy. So the vacuum energy will be function only of the flux numbers. Okay. And then the question is, what's the functional form of the lambda in terms of the fluxes? Okay. So, well, the fluxes can take any number, some range. And let's take a smooth or uniform distribution. For our purpose, it can be from minus 1,000 to 1,000 or minus 1,000,000 to 1,000,000. And it depends on the details of the particular model. So the nj will be parameters with some smooth or uniform distribution over some range. And then once we know this, and we know this functional form, we can calculate the probability distribution of lambda. And we can look at that distribution, okay, as we sweep through allow the nj. So this is a very generic way to calculate solutions of string theory. Why string theory have no free parameters, and yet we can calculate various properties from it. Okay? And of course, there's many, many, many solutions, as we can see, because typically number nj is order of hundreds, and each one can sweep through some range. Depends on details. The range can be rather large. And so the number of possibility is huge. And I should say, for some nj, there's no solutions. So we only take the cases with a local metastable minima. Okay? So this is the basic program. And the question now is we want to know what's the probability distribution P of lambda as we sweep through all our values. Okay? Well, the key I want to say is that P lambda tends to peak at lambda equals 0. Okay? This is nothing to do with physics at this moment. It's generically, with a little bit input from physics, this is statistical property, probability property. Okay? And when I say peak at lambda equals 0, I really mean it diverges. Okay? That means the probability distribution diverges at lambda equals 0. Okay? So this is the basic idea. If lambda have some generically functional form, and we will see that the generic functional form will have this property, then we see that small lambda may have a preference. Okay? So I will give you very simple examples first to motivate what's going on. Okay? So let's consider a random variable, a set of random variable xi, and let the probability distribution xi be uniform in some range. So question, what's the probability distribution of its product? Okay, if z is a product of some of them, all raised to some power. Okay, these are simplest functions. Well, we can easily calculate because given probability distribution this normalized, and then we can say z is function of this, and then we can easily calculate this and obtain pz. So its calculation is very simple in general, unless the function becomes very complicated. Okay, so I will look at simple functions, and get some idea what one can expect. Okay, the simplest function we can think of is that take z equals x1, x2. So x1, x2 both have a uniform distribution between -1 and 1, uniform. And the product of two of them is the red curve. Okay? The red curve, it diverges at 0. Okay? Naturally. So even x1, x2 is uniform, the product has a probability distribution that diverges 0. And you have a product of three of them, then it diverges more sharply. Okay? And we would like to consider something with a factor of hundreds. Okay? So it will be peaked very sharply at lambda equals 0. This is just very, very simple issue. Now, the distribution of the x1, x2 here is uniform. This is not necessary. You can take a Gaussian distribution, and the divergence is the same. Okay? The 0 is a preferred position. Okay? You can even take a power, and the power also very clearly diverges 0. So if it's a function of a positive power larger than 1, then it diverges to 0. Okay? So again, 0 is preferred. I should point out in general, I take symmetric shape, but you don't have to. If the distribution of x is something skewed, the divergence again is always at 0. It's not peaking at anywhere else. Okay? So this is again a very clear point. Let me take another function. Suppose the probability distribution of the x, the input parameter, diverges peak at 1. So if I consider z to be a function of x1, x2, if x1, x2 both peak at, and diverges at 1, then when z go to 1, it will go to x1, x2 both at 1. So what happened to the distribution for the product of x1, x2? Well, it doesn't peak at here. It peaks at 0 also. So that means choice of 0 is a very simple probability property that is very easy to see. Okay, so with this, let me go back to, you can think about many other functions. It's a good exercise to think up some functions, when it will peak, when it will be sharply peak, when there will be no peak, okay, at 0. But I should point out, whenever there's a peak, it's always 0, not anywhere else. Okay, so you can look through many functions, and it's good exercise to play around with this little exercise. So the peak is either at 0 or no peak. So I would like to introduce some sort of measure, which we want to calculate cosmological constant with a large sample. We would like to look at the average. But turn out average is not the most interesting thing. The interesting is the median. So we will look at the median, and we generalize a little bit called lambda y%. Lambda y% is the value where y% of the solutions have a value below y lambda 0. So this is a slight generalization of what we call median. And median will essentially be lambda 50%. Okay? So what we're interested in is maybe the ratio of this is a good measure of the preference for small lambda. Okay? So it's just a way to see how peaked it is towards 0. Okay? So let me give you a very simple example which illustrates what we're going to see. Is that suppose I have a million solutions at lambda equal 10 to the minus 9. But one solution lambda equal to 1. Then the average is clearly 10 to the minus 6. But lambda 50% is 10 to the minus 9. Okay? So that's very simple. But if we now move the median solution down to 10 to the minus 20, but still have the one solution at lambda equals 1, then the average doesn't change. But the median value dropped to 10 to the minus 20. Okay? So that means also in this case means that the likely value is 10 to the minus 20. Okay? And of course, in this special case, lambda 10%, 9% also 10 to the 20. So I just want to give you a flavor of what kind of feature we want to have. Now, before I go further, I would like to say what kind of behavior we won't get a peaking at 0. Okay? So if the potential has two terms, they are not coupled to each other, then naturally lambda would be sum of the two terms. And in this case, typically it's no peaking. Okay? That means that there's no preference for lambda goes 0. Okay? Even if individual terms have a probability distribution that peaks at 0. Okay? So that's another very important problem. Okay? So now the peaking of probability distribution at 0 is necessary. Okay? In fact, to get a very small lambda, it has to be very strongly peaked. Okay? But not necessary, not sufficient sometimes. Now, however, these cases where the peaking is not present doesn't really happen because gravity coupled all sectors. So all of them should be coupled at least by gravity, if nothing else. In fact, in string theory, it's also coupled by the dilettone, which give us the coupling. Okay? So, but it may happen in oversimplified model. If you take model which is oversimplified, this may happen. So we go back to Busov-Polchinski case, it's sum of terms. Now, if you look at individual term, because it go like n squared, so actually each individual term will have a peaking behavior at 0. However, if we add them together, okay, you find that this one has no peaking at 0. Okay? It will have values, but there's no preference for 0. Okay? So this is important that in an oversimplified model, the peaking's behavior. We have to couple the different sectors together. Okay? And the coupling, bring them together is crucial. So now I go to string model, but I'm not going to go to detail of this, but rather to demonstrate that in the last 5-10 years, string theorists have worked very hard to construct, to work out the terms in the Lagrangian or in a supergravity approximation. So we can finally go ahead and calculate the distribution and lambda for different solutions. Okay? That's not possible. I would say 5 years ago, that's not quite possible. Okay? So this, again, is a development by many hardworking string theorists. So we see the following. The details not important, but rather the flux come in, where F3 and H3 come in many, many terms. So typical compactification is very complicated Calabi-Yau and have many, many cycles of order few hundred. And in each cycle, you can wrap these fluxes. Both fluxes you can wrap around. And so we will have many flux number coming in and many moduli. Okay? So this is essentially the basic picture that we have. Okay? And different compactification, we have different number of fluxes coming in and different number of moduli coming in. And anyway, these are the details people have worked out. And we take some approximation, which justify in some particular situations. And essentially, we take the models in what people have constructed instead of creating some toy models. So important point to realize is that each of these compactification, these are some of the ones that people have studied relatively carefully. We don't need to know what they are, but you know is that the H11 is the number of volume sizes, okay, that control, called Kähler moduli, which control the size of the volume of the 6-dimensional compactified Calabi-Yau manifold, or Calabi-Yau-like. H21 is number of shape. So once you compactify what the shapes it is, so hundreds typically, and for each of these complex structure moduli, the shape moduli, there's probably generic, there are 4 fluxes to go with it. Okay? So we can see hundreds of fluxes. Okay? And in these typical models, we can now study in some approximation what the lambda is and what the probability distribution of lambda is, and see how likely small lambda can appear. Okay? So we study 3 cases. In first cases, we only have one simple Kähler modulus, the volume, okay? But in a non-trivial potential that people study. And so this is only one specific case. And we find that the average lambda is 10 to the minus 7. This just set a scale. Everything measured in Planck scale. We should say everything should be measured in the string scale, but string scale, Planck scale differ by a factor of 1 or 2 order of magnitude only. So And the median value 10 to the minus 19, but 10% of the solutions have a value which is 10 to the minus 54. Okay? So it's a very small number. Without going into too much detail, it's actually the racetrack, so-called superpotential, but potential like this. And the reason this happened is because it's raised to a very high power. Okay? So we take gauge group, which is, say, UN for n equals 25, which is a reasonable number. Okay? If we take it bigger, we can get a much more suppressed lambda. So this is just one example here with no dilaton, no complex structural moduli. The next example we want to study is there's many complex structural moduli. Okay? As we say, it should be order of 100. So in this case, in a simplified model, we find is like 10 to the median value is 10 to the minus roughly number of complex structural moduli. So if it's 100, then we get a very small median value. Okay? Now, I should point out that the average is stay 10 to the minus 8. It doesn't go down with age, which is important. Because in the calculation we do, we have to take a number of approximations. And it's always important that we're not throwing out a large cosmological constant. Large means close to Planck scale values out. Because you can easily throw out a large lambda, then you only get small lambda values. Okay? And the fact that the cosmological constant average stays at a number which is not far from Planck scale indicates that we have solutions we have not thrown out. Okay? It's just such that the distribution prefer very small lambda. Okay? So that's why we have to compare the average versus the median. Okay? If the average also is going down, then that means that we are probably throwing out the solutions in the approximation we're doing, and then we cannot claim that there's any preference for small value. So in this, so I'm not going to give detail. So this is, but the detail does tell us that the functional form is rather complicated. But on the other hand, it mimics a little bit like the product instead of a sum. Okay? In the boosted projective, where we sum over terms, then there's no peaking behavior, no preference for small lambda. But in the cases here, it really becomes like more like a product of terms, okay, and raised to some power. So this is roughly the value. The red dot is the average, which stays constant as we increase the number of complex structure moduli. This is 80%, this 10%, 50% is here, and the 50% essentially give the value I gave, okay? Okay. So, and here we only measure, we can calculate only to 30. It's very difficult to calculate higher. And if you look at more coupling, stronger coupling, people have looked at these models with 2 complex structure moduli instead of 30. And they have to use a Fermilab supercomputer to do it. Okay, so it's relatively non-trivial. And also that if the number of moduli is small, less than 5, you haven't reached the asymptotic behavior. Okay. So this is another challenge we have. So we look at a third case, which we look at supersymmetric cases. That's another example we have. And then we find in this case, the magnitude also goes down exponentially fast. Okay? But the average doesn't change much. For supersymmetric vacuum, KKLT is a particular scenario. Like for supersymmetric vacuum, the cosmological constant is always negative. Okay, that doesn't describe our universe. So we only take the magnitude here. And in this case, we see that the value again, the average stays up there, but the 50% or the median values drop exponentially, follow closely this behavior. Okay. So the picture now suggests that in the models that people have studied, semi-realistic, some approximation, that it's not hard to get the median value to be exponentially small. But the average stay high. Okay? So what we can say is that the peaking of the probability distribution of lambda at 0 happens for both positive and negative lambda. And for negative lambda, it's quite interesting because you expect energetics will prefer more negative cosmological constant because they're more energetically favorable. And yet, the statistics tells us you prefer to be very close to 0. In fact, 0 is the highest possible value for these solutions. Okay? So clearly, energetics is not driving what's going on, but it's the statistics that's driving it. And if we introduce many complex structure moduli and racetrack, then it's clearly we can quite easily get the lambda as small as 10 to the minus 100 or smaller. So usually what we worry about is, well, if I introduce quantum correction to it, that will shift the lambda. But in this framework, the quantum corrections have to be introduced. Say, electron loop contribute to vacuum energy is something we do. What you need to do is to take the electron mass, the coupling, and convert it to functions of the moduli and the flux, put it in, and then calculate it. You cannot just introduce it without worry about the feedback, okay, the back reaction, which is crucial. Okay. And this solution also indicates that at high vacuum energies, hardly any metastable vacuum exist. Okay. All of them will be accumulating around 0, very much so. So what's the picture? Well, the picture is roughly following I would like to present, is that if you look at the Booster-Pocinsky, you have lambda all over, but more or less sort of evenly distributed for very large lambda and for very small lambda, positive, negative, around 0. There's no preference for any value. But in this statistical behavior, we find that there's hardly any solutions that's metastable at lambda that's not close to 0. Okay, so it's accumulated at 0, both positive and negative, and very sharply accumulated 0, but hardly any solution up there. So naively, we would say that, well, during inflationary epoch, we are very high up, but we'll roll down, depends on the shape potential, roll down fast or slow enough, not get trapped by any of the metastable vacuum because there's hardly any, essentially almost none. And then when you roll down to a very small value, then all of a sudden you find many, many solutions, both positive and negative around 0. And since you come from positive values, you probably get trapped at positive value more likely than a negative value. So that's really the picture that we like to envision at this stage. Okay. So the question now is, how robust is this statistical preference? Well, we have to examine many other models before we know. Okay. As we understand string theory better, we can calculate more interaction terms, and then we can feed it in to see that how likely it is. But we're optimistic for the following reason. If the different sector we simplify enough such that they don't couple together, then there's no peaking. The peaking will come only if they couple together. As we show in the case with sum of terms, they don't couple together, there's no peaking. But once they're coupled together, then instead of sum of terms, they would be more like a more non-trivial function. And in the case that we have studied, they will bring a peaking. Now, if you couple even more strongly, what will happen? We don't know. Okay? But if you couple more strongly, if there are 100 fields, they couple strongly, well, by more terms, all with each other, then you can easily see that the equations are very, very difficult to solve unless numerically. And that's actually the problem we are facing. So it's a technical issue that at the moment we look at cases where we can solve and they couple together and we see clearly there's a sharp peaking. But will that peaking stay there as we couple even more interaction terms remain to be seen. Okay. So thanks.
Is it correct to say that the assumptions of the string theory that you presented still need to be fine-tuned in order that there could be statistical preference for
no.
very small?
No, there's essentially no fine-tuning because there's no free parameters. The only thing that come in is the flux numbers and the moduli value. And the moduli value are solved in terms of flux numbers. And so you take a particular set of flux numbers, say 200 of them, you fix a particular value for each one, and you calculate the minimum by solving for the values of the moduli, and you calculate lambda. And then what we do, we sweep through the flux numbers. So from that point, there's no free parameters. I should point out that in some cases, there are parameters which functional dependence of the flux numbers are not known. So we have to rely on geometry to see that the fact that they can take particular range is justified by geometry. But essentially, first approximation, any parameter we don't know what it is, we treat it as a random parameter with a probability distribution, a smooth one. So there's no fine-tuning in the case. But I should point out, for many choices of the flux number, there's no solution. So we only have to look at the cases with solution.
The assumptions for your theory, I'm not asking about. I'm saying the assumptions that's required for your theory, is it still that some fine-tuning is required?
So I should say, you see, this is what the potential will be, okay? So how many moduli coming in and how many fluxes come in depend on geometry. But in approximation, we have the detail of the particular manifold geometry is next order. We don't include. So what we have is generic interacting fields such that apply at this level of approximation to large class of geometry. So here, there's no, in the sense here, there's no free parameters there. No, except for the fluxes.
Well, it's very nice to have the cosmological constant. But if we look at the particle physics, we have many unknown mass parameters. Therefore, my question is that if we have the solution to this problem, then solutions of other mass parameters come together or independent?
Yeah. So at this moment in string theory, we have not found a vacuum that describes our universe at the moment. They find many which are close, but not our universe. So if we look at those models, then all the mass parameters, including mass parameter in principle or standard model or something like the standard model, are actually should be calculable in this case. So for example, masses will couple to some of the scalar fields like Yukawa coupling and general models. So, here we do a more generic case. And if you say that I have a mass parameter coming in, then you have to convert that mass parameter to a function of both nj and ui, and then rewrite this. And that's important. Otherwise, you find a solution, very small cosmological constant, and you add the one loop electron, then already change it. So you have to take that correction, if you want to include to it, rewrite it in terms of the flux and the moduli, whatever, and then feed it into the potential. And that just shifts the distribution, but doesn't shift the preference for zero.